Today we are discussing Heine-Borel Theorem in Rn, which is the most important theorem in topology. A subset of Rn is compact if and only if A is closed and A is bounded, whether the metric is Euclidean or the metric is square. Before discussing the theorem, we are discussing Euclidean metric and the square metric. A Euclidean metric is the usual distance formula, like for 2 point x1, x2, xn, and for y is equals to y1, y2 up to yn, dxy is under root x1 minus y1 to the whole square up to xn minus yn to the whole square. Example: circle and sphere. In a square metric, x is equals to x1 up to xn. There are 2 points x and y. In a square metric, the square metric measures distance using the largest coordinate difference. What is largest coordinate difference? Like for 2 point x is equals to x1, x2 up to xn, and y is equals to y1, y2 up to yn. A square metric is denoted as the rho xy, which is the largest coordinate difference between 2 points x1 minus y1, x2 minus y2 up to xn minus y1. And there is a relation between Euclidean metric and a square metric. Is the Euclidean metric is greater than or equal to square metric and less than or equal to root n times the square metric. Now we will discuss what is Heine-Borel theorem in Rn. Step 1. The key idea of this theorem is A is compact. We will prove that A is compact implies A is closed, and if A is compact, we will prove A is bounded. In forward part, let A be closed, and we will prove that A is bounded. Or firstly we will prove if A is closed, in forward part, firstly we will prove that if A is compact implies A is closed. We know that every compact set in a metric space is closed. Then every compact set in a metric space is closed. Since A is compact in Rn, so by the result that every compact set in metric space is closed, so A must be closed. Therefore, A is closed in Rn. Step 2. If A is compact, then A will be bounded. Now from the previous relation says that Euclidean metric is less than or equal to square metric, greater than or equal to square metric, and less than or equal to root n times the square metric. The result says that a set is bounded in D is bounded in rho. So we can prove everything using rho only. We will consider an open ball centered at 0 with radius n. We consider an open ball centered at 0 with radius m, such that n belongs to all positive integers. As n increases, this ball gets bigger and bigger. So every point in Rn lies inside some open ball. We want an open ball cover of A because compactness is defined using an open cover. A set A is compact if and only if there exists a finite subcover. Since A is compact, we create an open cover of A, apply compactness and get a finite subcover. We use an open cover because compactness only works through an open covers and it lets us swing an infinite curving into a finite one, which gives a boundedness. So since A is subset of Rn, so these balls form an open cover of A. Since A is compact, because A is compact, so there exists a finite subcover. So a subset of an open cover centered at 0 with radius m for some large m. Step 3. Now, step 4. We define an open cover in a square matrix as is the set of all x belongs to Rn such that the distance between x and 0 is less than of m. The row ball centered at 0 with radius n is the set of all points in Rn such that the distance between x and 0 under metric row is less than m. So, for every m x belongs to A, for every x belongs to A, the distance between x and 0 less than of m. Similarly, for every y belongs to A, the distance between y and 0 is less than or m. So by triangle inequality, the distance between x and y is less than or equal to distance between x and 0 comma y and 0. We already see that the distance between x and 0 is less than of m and distance between y and 0 is less than of m. By using two results, we can say that the distance between x and y is less than or equal to 2m. Hence, A is bounded. So, we already proved that. Hence, A is bounded. Therefore, compact implies closed and bounded. Now, we will prove that closed now we will prove that closed plus bounded implies compactness. Bounded means the distance between x and y in square matrix is less than n for some n. For all x, y belongs to A. Let x not be a fixed point. For some fixed point, rho x naught 0 is equals to b. So by triangle inequality, rho x 0, that means distance between x naught and 0, by triangle inequality, the distance between x and 0 less than or equal to distance between x and x naught plus distance between x naught and 0. The distance between x and x naught is n and it is b. Let it be the equation number 1. Let p is equals to n plus b. Then the distance between x and 0 less than or equal to p. Now recall the square metric. Definition of square metric. The distance between x and 0 in a square metric is the maximum coordinate difference. Here we take the distance from x to 0. So we take the maximum of x1, x2 dot dot xn, which is less than p. This means x1, if maximum of these is less than of p, then all the distance is less than of p. This means x1 less than p, x2 less than p. Similarly, xn less than p. So all x, that means xi less than p. Xi less than of p greater than of minus p for all I. So xi belongs to closed interval minus p to p. So x is equals to x1, x2 dot dot xn. We are assuming that x is equals to x1, x2 dot dot xn. So x belongs to, if x belongs to x1, x2 and xn, then x belongs to minus p to p cross, because each coordinate belongs to p, so x belongs to minus p cross minus p comma p cross minus p comma p, which is n times, because we are assuming that x is equals to x1, x2 up to xn, and each xi belongs to minus p closed interval minus p to p. So x belongs to closed interval minus p comma p power n, and x belongs to, we are we are defining that x belongs to a, therefore a is the subset of minus p comma p power n. A is the subset of minus p comma p power n. Since minus p comma p is compact, or n is compact, because it is the finite product of compact set is compact. Since we know the finite product of compact set is compact, and it is the product of finite set, finite compact set. Therefore, minus p comma p power n is compact, and A is closed. So closed subset of a compact set is compact. A is the subset of Rn. So closed subset of a compact set is compact. Since A is the subset of minus p comma p power n, and this is compact, so A is closed, and closed subset of a compact set is compact. Therefore, we conclude that A is compact. Therefore, A is compact. And hence we are done. Thank you.